Welcome back. Today we will finish the portion on cushioning. We will do an example. Based on that example, you'll have a homework assignment on this. It should not be long. It should be just some calculation to be done. And before we start, I wanted to talk to you. I mentioned a few times I forgot about bringing some samples I had as well for loose fill and new things that exist. Some may not be looking so cool, but they do work pretty well. There's two different products I want to show you. So this looks like little corrugated French fries. It's called Corfill. Actually, there's a guy who makes that in Florida here. He just shreds these, but as you see, it's just like holds together really well. And that's one material that we did test in the past, but it's an interesting thing as for loose fill. Obviously, it has the disadvantage of like peanuts that it's everywhere. Okay, but can be recycled or composted. And it does work very well. It just creates like those nests, if you want, for whatever you have in the box. So it does do pretty cool stuff. And I don't know if you guys seen these. If you guys want, I can have a few going around. But these are called expendos, okay? And they are these little triangular, let's say, this triangular prism. I think I can have more going around. Oops, you can play with them, you can break them down. And they're pretty cool. And one of the reasons why I think they're cool is that the way that they are made. So the idea with these, there's different weight or caliper of paper that are available, depending on the weight you have. So you can imagine if you have a bunch of these, they kind of just interlock together and create that dunnage material. So the idea for these is oftentimes you have a box, you put some in there, you put your product, you put some more on top, and they create that matrix, if you want, of structure that should not shift around like peanuts would do, okay? Because they catch between each other. The other cool thing is that if you're dealing with Corfill or peanuts or everything else with dunnage except maybe for like airbags, is that you have to store this stuff, okay? And like peanuts, they take huge space, okay? These are pretty cool because they come on a roll. You think about, for example, like drawing tickets that you can have, like you have a roll. It comes on rolls like this, and you have a machine that erects them automatically. So the roll goes, and it's just like you have those expendos that falls off. So it's a nice thing for inventory and storage of this. So you don't have to store like ginormous bag of these things. So you just have a machine, and you have rolls, and as many as you want, you just run the machine and it's basically create these things. So they're pretty cool. And again, they exist in different sizes and things. Any of you seen that before? You learned something. And again, it looks a little bit better than this. I'm not sure if it works better than this. Okay, it depends always. Good. So last time what we did, we introduced a few things. We talked about new few concepts. So the static loading that we needed to define and use. Static loading is the weight of your product you're trying to cushion. And by the weight, I mean not the mass. I really mean the weight, mass times gravitational acceleration. So we have a force here divided by the area of the cushion. Okay. And the area of the cushion here, I remember what we talked about, is really the area of the cushion that is applied on the product itself. Okay, does it make sense? So it's the area that is what's the proper word for this? I don't think I can remember this, but so it's really the area. Let's say the bearing area of the product is there. Whatever area on the area of the product that has cushioning, that's the area we're looking for here. So then we talked about cushion curves and what they look like. Okay. So we already addressed the fact that behavior of cushioning materials will change based on the number of drops. Okay. So the way that oftentimes they are represented is you're going to have a cushion curve for a first drop, second drop, third drop, and an average. Okay. So each of these cushion curves will be for a given drop height. You see here, this is for a 12-inch drop height. And on each of these cushion curves, you have curves for different thicknesses. Okay? And the goal with these curves, if you have them available, is to be able to find both the thickness of cushion you need and the area you also need to provide the adequate protection. Now, all these are created, if you remember, they oftentimes are smiling at you this way, okay? So the way why they are created this way, what do they have this form, is the way they are created, okay, is really, you have a fixed thickness, a sample of the cushion, and then you drop a plate with a variable mass, okay, with an accelerometer, and you measure the acceleration upon impact. So you start with a very low mass, you drop it from 12 inches, you measure the acceleration. Then you increase the mass, drop it, measure the acceleration. So as you increase the mass, you have more and more deflection, therefore the acceleration, which is on the y-axis here, decreases to a point where there's so much deflection that it starts to bottom out, okay? Then you have an increase back, okay? Towards a higher acceleration. Now, this is described here. This is explained there. How do we use these? That's where we finished last time. So typically we need to identify, we have a knowledge of the fragility of your product. That means knowing what is the maximum acceleration your product can basically experience before it gets damaged. Once you have this, okay, you also need to know what kind of drop height you want to protect against. If you expect waist-high drop height around 30 inches, that's one thing. If you think that something's going to be carried on their shoulder, or it's going to be dropped from higher, or it's going to be stored on a high shelf and it might fall, or things like this, you can adjust it. But once you know the drop height, you pick the cushion curve you want to deal with. So drop height, you want to protect from multiple impacts or a single impact. That depends on what you want to do. Oftentimes, multiple impact might appear to be the best solution because it's likely, depending on the drop height, obviously, that you may be faced with multiple of these impacts. So, knowing the drop height, selecting the right graph, and knowing the fragility of the product, let's say in this case was 30 G, so you draw a line, horizontal line that crosses this. Now, that line allows you right away to pick the thickness, okay, of your cushion for that drop height. Every thicknesses that are above that line all correspond to acceleration higher than your threshold. So it's not going to provide you enough protection. You need to take the smallest thickness that will provide you with enough protection. In this case, it will be 4 inches. Then you have to select, if you want to find the proper area through the static loading. We mentioned that at the bottom here, that will be obviously the most optimal protection. If you want to have a cost-effective solution, which is often what you are after, so you want to take the largest static loading, which will be the intersection of your critical acceleration and the cushion curve for the thickness you selected. You go here, that corresponds to a larger static loading. That means you divide by a smaller area, and that will give you a protection with a smaller area of cushion. So, any question on this? Good. Bless you. So another method that is sometimes used is what's called a stress energy method. And why are people starting to look at alternative methods to cushion curves? Because think about this. Okay, you have to sample of cushioning material of a bunch of different thicknesses. You have to test them with different mass. Okay, maybe around 5 tests each for different drop heights. Okay, so it's a lot of tests to run, okay, to characterize a certain type of material for different thicknesses. So one approach that has been used in a way, it's a little bit of a similar to what you've seen in many cases in engineering where they use non-dimensional numbers, right? And they look at, for example, the relation between the drag coefficient or the friction factor and the Reynolds number. Instead of running tests for different viscosity, different velocity, different density, and all, if you're able to regroup them together and make physical sense of how these numbers work, you can regroup everything into one curve, okay, that will match everything. In a way, it's a similar approach that is used here. The stress energy method relates a bunch of things all together. The peak acceleration and the static stress, the drop height, and the cushion thickness, all together here, okay? So what is done is that you have y and x, okay? And then you basically fit a curve to a series of points. So you will run a few different drop heights, different thicknesses, and so on, and you'll get a series of points like this, okay? And the idea now is to fit that exponential curve, okay, that will basically match the behavior. And the idea behind this, I don't want to get too much into detail, just to show you that it exists. There's still people doing some research on this. But the idea is that with one equation, you should be able to describe the behavior of your material, whatever the drop heights and dimension and things like this, instead of going through cushion curves. Does it make sense? Okay. So other parameters to take into account when you design your cushion are cushion buckling and also cushion creep, okay? So this is obviously exaggerated, okay? But buckling, okay, basically when you have your cushion that is in a way compressing or failing not in a uniform manner, may happen, and is likely to happen, if you have a area that would be, let's say, that would be the opposite. But if you want to avoid this, you have to pick an area with a relation to thickness that will satisfy this. In a way, if you have like a very small area and a thick cushion, it's likely it's going to buckle. And that depends as well of the weight distribution of your product, obviously. So if this happens, then your cushion is not necessarily going to work properly, okay? And you may have shifting into your packaging system, which you don't want to have, okay? Cushion creep, okay? Some of you may have done, I have a few mechanical engineers here, they should be like very good with understanding creep, okay? But what you have is that cushion are, I would say, we treat them as elastic, but oftentimes they will display some viscoelastic behavior. That means if you were to expose a cushion to a stress for a long period of time, let's say you have your product that is relatively heavy, sits on a cushion, and you have this in storage for a few weeks, okay, or more. So what's likely to happen is that if you have that constant stress applied to the cushion, you may have a very slow but consistent deformation that occurs with time. That's what's called creep, okay? So if it does happen, then you may reduce actually the thickness of your cushion during that storage period, and your product may not, your design, I should say, may not perform as well as intended when it's time to do that. So part of the other thing as well that may affect creep is also temperature, depending of your type of material selected, particularly if it's plastic base and if it's a foam. If you have high temperature during storage, for example, you may have a softening of your cushioning material and you may have more extensive creep problem that will creep through your distribution process. But anyways, yeah, so that's something that may happen as well. Yes.
How come that formula doesn't have like the mass of the object, or because if you have like things that are protected, like it could be paper versus like metal. The metal, like shouldn't there be like properties of the system in that equation?
Um, I think this. I don't know exactly.
Does that make sense? What I'm asking? Because it doesn't take into account like paper cushioning versus like metal cushioning.
But you're not gonna have metal cushioning.
I don't know.
But
Okay, like plastic versus like
okay,
paper or that stuff.
but yeah, I see what you're saying, but I'm not entirely sure. Okay, that's a guideline based on area and thickness that is likely to do that. I can look into it. Okay, but obviously, for a certain, let's say, K value, regardless of your material, okay, uh, I think these parameters should take into account the buckling problem, regardless of what it is. Okay,
Mhm.
obviously, if it's stiffer
Yeah.
than other, that might not be as much of an issue. But as a rule of thumb, okay, that will be something that will be a useful tool. Good question. So once we have established the area of your cushion that you need, the thickness as well, so you guys, okay, have to decide what will be the configuration of that cushion. And that depends on a lot of things, okay? You can have different cushion, different parts if you want, that will give you the total area you need, okay? So you can have a face pad and an edge pad, for example, and you can have one on top as well, but as long as the total area matches what you establish, it should be good. Obviously, it will depend, okay, as well of your weight distribution of your product. If it's pretty uniform, or if you have, like, for example, a heavy power supply on one side, okay, that's something you will have to test, okay? Do some analysis and look at maybe you need to have more cushioning material on one side, less area on the other, and test it in the lab. Obviously, you can do calculation to test it as well before you go in the lab to try to have a uniform distribution of that cushion with respect to the weight distribution of your product. Yeah, but that's something you have to think about. And again, you have basically sky's the limit on this, depending on what you want to do and how the product is designed, and if you want to have multi-component or one component, and so on. But that the idea is to then pick the cushion that you want to design and test it. So, in general, let's see. What are the steps you have to do, okay, to successfully select or design pick the right cushioning for your product? Obviously, you have to know your product. You have to determine the fragility and characteristic of the distribution environment. So that means maximum acceleration, estimate the number of impacts, okay, vibration, temperature, relative humidity, and in all of this, that includes, is it going to be road transportation? Is it going to be going on airplane? What are the different steps? How many manual handling you're going to get, etc., etc. So we need then to calculate the thickness and the area. So what you may have to do as well, you may have to investigate different material. Okay, obviously, if through your company you have your distributor and you've been using one type of cushion forever and ever, okay, that's something that might be restricted because you may have good pricing for that supplier. You're going to be able to get what you want for the best price with one material. But always helps to look around and see what's available, okay? And the idea is, obviously, your cost should be reduced as much as possible, and typically as well, thinner is better, okay? And you remember why, okay? Because if you need to have cushioning on all surfaces of your box, additional inch on each side, change the volume quite significantly, okay? So you need to have thinnest material possible. So, what are the other concerns you need to identify? Gradual loss of thickness due to creep, non-uniform compression, cushion buckling, temperature and relative humidity effect. Okay, that's true. Temperature if you have a polymer-based material, humidity if you have any types of paper-based material, that will be important. Vibration. Okay, remember that we started, when we talked about vibration, we had a system which was a combination of a cushion and a product. And we saw that this system had different behavior based on different input vibration. So obviously we pick a cushion for shock protection, but we need to look at how it's going to behave when it's exposed to vibration. You want to avoid any natural frequencies and combination that will create potentially damage due to vibration. So test the design, and depending on the results, go back and improve it. Avoid over-packaging. That's always going to be what your boss is going to tell you, most likely, okay? No one wants to pay for packaging, even if you're dealing with expensive product, okay? So study the behavior in actual use. That means you can do a real shipment, okay? See how it's going to happen, how it's going to behave. Depending on the behavior, go back and improve it and avoid over-packaging. So packaging design, in a way, it's not a, as you can probably understand by now, it's not a accurate science, right? What we try to gain through the semester is some tool based on physics, okay? Hopefully a rational approach to give us some hint, okay? To guide us through the design. But most of the time, you'll have to test it, okay? Analyze how it's behaving and redesign it and test it again, do experimental shipment, and always try to improve and analyze. Obviously, it also depends on the industry you're working with as well. So some industry, you don't have much, I would say, restrictive guideline or law to follow. If you're shipping an engine part or something like this, it doesn't matter. If you're shipping medical devices, okay, you have standards, okay, you have FDA rules that you have to follow, and you need to have validation process in place, okay? And once it's in place, you can't change it, okay? I mean, you can change it, but it's going to cost you thousands and thousands and thousands of dollars to do that, okay? So you don't necessarily want to do it, okay? So you make sure that whatever you design, okay, works. And oftentimes that's one of the issues with medical devices. It's they don't want to change it because it's too expensive, okay? Once it's qualified, once it's validated, okay, change is really hard to happen. But other field, you may want to be able to always change it and update as much as possible. Any question on this? Good. So the next thing I want to do is do the little problem example I distributed last time with you. If you don't have it, I don't have the extra slide with me, okay? So you'll have to follow what I'll be doing. I can show you though on the board here. Okay, so again, this is a simple, not a very fancy story, okay, just to illustrate the point. So what you have here is that you have to protect a cubic product of 25 kilograms, so 30 centimeters per side against shocks. Through a series of tests in the laboratory, the following damage boundary curve was obtained for the critical orientation of the product. So that means you tested a bare product, okay, and you establish its fragility. Okay? For your design, you decided to use Ethafoam 220 polyethylene foam for multiple drops from 75 centimeters, which is about 30 inches. calculate the thickness and area required for the ethicone cushion. Okay, so it's going to be very similar for your homework example, and you're going to have a problem like this on the exam as well. So, what we have so far, okay, we have the mass, which is 25 kilograms, okay. Our product is a cubic product, okay, 30 centimeters, so if you want 0.3 meters per side, okay. So you want to protect against a drop height of 75 centimeters, so 0.75 meters, which is about 30 inches. So you have the damage boundary. What information do we have from there? Okay, we have two things, right? Okay, so we can find the critical acceleration and also the critical velocity change. So what would be the critical acceleration from there?
95, 93.
Yeah, 92.5.
Wrong. It's 92.5. Yeah, sorry. Yes. So an exam is going to be roughly, okay, you're not going to get, if you were given a damage boundary curve, okay, it's not a problem if you were to say 93. In here, I did my problems with 92.5 Gs, okay. So if you put that in meters per second, you don't need to do that necessarily here. So let's do it like this. And you also can find the critical velocity change. In this case, bless you. If you go back down here, you get a critical velocity change of 2.5 meter per second. Okay. So, let me blank this off so we have a little bit more space. One of the questions I may ask you, or you should ask yourself, do you need protection? Okay? Do you need a cushion in this case? So,
Yeah.
are you sure? How
If
do
there-
we know?
If there's a line on the graph, that means that there's a boundary between the thing breaks and the thing doesn't break.
Okay, but it depends, right? So, if you remember, your damage boundary curve looks something like this. Okay, so if you are here, okay, if you are past the critical velocity change, you will need protection because depending on the drop height, okay,
Yeah.
you're likely to get in that damage. But if you are here in that region, okay, you might not need any protection. Even if you get large acceleration, it's not going to get damaged. So, what we have here is 2.5 meter per second is the critical velocity change. So if we are dealing with a drop height that corresponds to a velocity change larger than this, that means we need protection, okay? But we need to check that first, okay? So, let's see. Get my solution, okay? So, let's first verify if we, I should say, if the product needs protection against a drop of 0.75 meters. Okay? So, if you drop something of any height, okay, we discuss what's going to happen at impact, right? You remember when we talked about the coefficient of restitution? Any of you remember what is the coefficient of restitution? Nothing. Okay.
Velocities.
It's E. Velocities. What about the velocity?
Rebound velocity divided by impact velocity.
Okay, good. Okay. So the coefficient of restitution tells you, okay, if your packets fall, is it going to rebound? It's the ratio of the impact velocity to the rebound velocity. Okay? So typically, the minimum velocity change you will get, okay, with a certain drop height, is if your product falls and boom, stays there. You agree with me? There's zero rebound velocity. So let's look at this. So the minimum delta V min, okay, corresponds that if there's no rebound velocity, okay? So that means, okay, delta V min is equal to what? If there's no rebound velocity, the total velocity change associated with an impact with zero rebound velocity is equal to what?
0.
Impact velocity, very good, okay? That'll be equals to VI, which is square root of 2GH. I told you we're going to see that equation many times, okay? So if you calculate this, okay, that'll be square root of 2 times 9.81 times 0.75. We find that delta V min is equal here to 3.84 meter per second. Okay? So, that implies, okay, since delta V min is larger than delta V critical, okay, protection is needed. Okay? Does it make sense? Yes.
Doesn't it have to be over delta V, the critical delta V, and the critical acceleration for it to be damaged? So like in that area?
Yeah.
So we would need to take into like the two consideration, like.
So the thing is, if you are here in that zone, so that means if you're below the critical velocity change, whatever acceleration you're going to get, okay, you're not going to get damage. Does it make sense?
Yeah.
So if you're here, okay, you're right. I think if I understand, you need to go in that zone, okay? But if you're here, if you're past this, that means that impact has potentially enough energy to create damage. So depending, okay, of the acceleration you get, you're potentially going to potentially get damage. So if you are past this, you cannot risk not having protection because the chances you're going to get there are going to be pretty high. Okay, so that's what it means. Does it make sense? So if you are dealing with a minimum velocity change that is larger than the critical velocity change, you should have cushioning to prevent in the occurrence of damage.
Wait, I have a question.
Yes.
Okay, two questions. It says, let's first, what's the third word? Rely?
Let's first verify
Okay.
if the product needs protection against a drop of 0.75 meters.
And my other question is, in the graph, does it always just go up? Because in my head, it would be like a linear relationship.
So it depends what you're doing, okay? So right now, when we design the cushion curve, when we learn how the cushion curves are, not cushion curve, the damage boundary curve are created, it's going up, okay? But during distribution transport, we don't know, okay? It depends on the impact, on what surface it falls, of angles and things like this. It depends, okay? That's the idea. So obviously, if I ask you a problem, okay, on a homework, okay, or on an exam, okay, and I may tell you that you have to verify for this. I may tell you that you don't have to check for this, okay? If you check for this and you say that your product doesn't need protection, you had a mistake somewhere, okay? Because if I'm asking you to do that, I want you to find the area and the thickness. Does it make sense? So don't think I'm going to ask you a trick question, okay? Does it make sense? I've done that mistake one time as I was a student. it's a trick question, and it's so bad this example. I still remember, it was an electron traveling between two plates, and they were asking where it's going to touch the plate, and I said, it doesn't touch the plate, that's a trick question. But that was wrong. So anyway, so if I'm asking you a question like this, okay, I may clearly specify you don't need to verify if you need protection or not, okay? Does it make sense? So I may say you need protection, find the area of the thickness. So that means I want you to do this, okay? So that means the next step, okay, is we have the drop height, and we want to test for multiple impacts. So on the little handout I gave you, you had a bunch of these cushion curves. So what figure will you gonna use for your calculation?
Figure 8.
Figure 8. Awesome. Not too hard, right? So multiple impacts, okay? Height about 30 inches, okay? So that means, okay, we need to use figure 8, okay? And on the homework and on the exam, I'm going to ask you to tell me specifically what figure you used, okay? Very important. Now, once we have done this, okay, the next step, and you can try it yourself. Again, I've done it. Depending on the copy of the paper, you may have different values, but we had a critical acceleration of 90 g, okay? So if you have a horizontal line through 90 g, I'm going to try to reproduce that, okay, here. So you have critical acceleration here, or acceleration G, and here you have static loading in PSI, actually. So your graph looks something like this, okay? Okay, this is 1 inch. This is 2 inches and so on. So 90 G, sorry. Okay, is around here. So you draw a line, okay, and you find that obviously 2 inches, 3 inches, and so on gives you plenty of protection, but too much. So from here, okay, we should find that a thickness of 1 inch, okay.
Why'd you pick 90? Just random?
No, I don't do anything, man. Oh, 92. It should be 92.5. Sorry. Sorry, guys. Okay. I don't know why. I jumped pretty quickly here. Yeah, 92.5. Okay. The thickness of 1 inch provide enough protection. So 1 inch should be identified. So sorry about this. Okay, so 92.5, you draw your line, and then what you have to find is typically this is good, this is all good, this is good too. Okay? So unless I specified otherwise, you need to pick the most cost-effective point, okay, here, okay? And then you're going to go down here vertically and read the static loading. So you might get a different reading than what I did for my calculation, but what I had here, okay, what I used was 0.55 psi. Again, don't worry about it, okay? If you will have picked 0.525 or something, you know, obviously if it's not way off, you're not going to get penalized because of this, because it's a graphical representation, and I understand it. Now the next step is that don't make the mistake. Remember, this is in PSI, okay? So the static loading that we have is 0.55 psi, okay? So we want to convert that into Pascal. So this is 6,893 Pascal for 1 psi, okay? If you calculate this, you'll find a value of 3,791.2 Pascal, and this will be equal to M times G over the area of the cushion. And this is 25 times 9.81 over the area of the cushion. So what we can find is the cushion area is going to be equal to 25 times 9.1 divided by 3791.2. We'll get the value here of 0.0647 meters squared. Okay, so now if you get a cushion area of 5 meters, that means you have an error somewhere. Okay? It cannot happen. It needs to be a rational area. It needs to make sense with your product. So, what would be something you will check once you get the area? Okay? So in here we get 0.0647 meters squared. What would be, if you think about this, what would you check next? Yes?
Would you make sure that the area of the cushion is the same or smaller than the area of the...
Very good. Okay? So that area has to be smaller than the face on which you're going to apply it on your product. Okay? Because if it doesn't fit on the product, that means your cushion is not going to be able to protect it. Okay? Because that, if let's say you have your product here, and let's say your cushion is like this. So your cushion is designed so the weight is uniformly distributed over all that area. Does it make sense? So if it's just in the middle, it's not going to do it. You're going to need a thicker cushion. Does it make sense? So the next step here is to check. Okay, so the smallest, they're all the same here. Okay, so in this case, they are all the same. Okay, area of your product is 0.09 meters squared. Okay, so that means area of the cushion is smaller than the area of the product, so you're good. Okay, you can fit the cushion on your product, and you should be able to get good results. So I'll let you time to finish writing this, and I'm gonna just, I would say, stress a few things that are new that we haven't discussed before. So in this problem, okay, we applied pretty much everything we have seen in the slides. We had two new things, okay? One of the first thing was to see if we needed protection or not, okay, based on the critical velocity change. That's something that is important to check. Then these problems it takes, not even 5 minutes to do these, okay? You know the fragility of your product. You look at the drop height. You look at if you want to protect against multiple impact or single impact. Once you know this, you just have to pick the right cushion curve that is provided to you if you have available. Okay? Once you have it, you draw the line with the right critical acceleration. Okay? So if I were to give you a value in meter per second square, make sure you transform that into G's. Okay? You draw a line. Okay? That line gives you the thickness. Make sure that it's clearly indicated what thickness you're using, what figure you're using. Draw a vertical line from the intersection between the critical acceleration and the static loading that is the largest. Why? Because it will provide you with the smallest area. So you can do the calculation as well. If you were to pick this one, you will find there will be quite a difference in size, okay, in your cushion. And it may or may not actually fit on your product. I don't know about this, okay? That will be something interesting to check. But once you have this static loading, if it's in PSI, as most cushion curve in the US are, you will have to convert into Pascal. This will always be given to you. Once you have this, you have to calculate the area of your cushion, and that's it. And make sure, that's the other thing, make sure it does fit on your product, that the cushioning area needed is smaller than the area you have to work with, okay, on which you want to apply. Okay? Does it make sense? Good. So today you should get an announcement with a little homework. And so make sure you come on Friday, because on Friday what I want to do is present and assign projects for the remaining of the semester. Okay? So I want you to be there, to be able to select. Hopefully everybody is going to be able to pick a project they prefer. And if you're not there, you're going to be assigned a project. Okay? So make sure you are here, and we'll do that on Friday. Okay?